All right, this talk is about applying a non-naturalistic theory to a particular field. And in my case, since I'm a computer scientist, it's machine learning because that's a field I know a bit about. And it's also interesting because it has more general implications for science as a whole. So this is actually related to theories of science, philosophies of science, of how science works. And in particular, it's related to the theory of inductivism. So inductivism is this idea that just based off of a few observations, comparatively, we can actually generate general principles about how reality works. So if you think about just how vast our universe is and how vast the time scale is, it's surprising really that we've been able to come up with these all-encompassing theories about our universe. I mean, our physical theories apply across the entire stretch of our universe, even though we've only observed a vastly small microcosm of it. So it's actually very surprising that inductivism works, that we're able to come up with these general theories, only observing things very close to us in small amounts. But this is how we think science works. It doesn't seem to strike anybody as odd that we are able to develop such broad theories. Everyone takes inductivism for granted. But it's not necessarily true that inductivism should work. The philosopher David Hume, he was mentioned in a couple previous talks, proved that it's not a necessarily true premise that inductivism or induction should work. A quick paraphrase of his argument is that assuming the future will resemble the past because it has in the past is circular, right? Because you're using the same principle to support the principle. So inductivism is not necessarily true, but everyone takes it for granted. So why should we? So since it's not necessarily true, we have to have a reason why we believe it versus the converse. And what is the converse of inductivism? Well, it's that we can't generalize at all from our observations, not even probabilistically. So everything is just what it is. So this idea that we can generalize these principles based on just a few observations is not necessarily true. It's a circular argument to just assume that it's true. And it's not just merely a philosophical argument. It's actually been proven to be the case that inductivism is not necessarily true. In machine learning, it's been formalized by a physicist named David Wolpert as the no free lunch theorem. And this theorem says, and it's called a theorem, but it's true, I mean, it's a mathematical proof, that no machine learning algorithm is actually any better than any other algorithm. They're all equivalent to random sampling when you average them across all possible problem domains. So this means that if our minds are algorithms, if we are essentially just doing machine learning in our heads, then inductivism is impossible. And if inductivism is impossible, science is impossible too. We can't actually generalize off of any observations. All we can do when we have an observation, all we have when we have an observation is just the observation. There's nothing more and nothing less. All right, so that seems very counterintuitive though. It doesn't make sense to say that we can't learn anything, infer anything whatsoever. But there is a reason why we can learn things. So to understand that, let's go to another principle called Occam's razor. It was first defined by a cleric named William of Occam, and he stated entities should not be multiplied beyond necessity. In other words, the simplest explanation for something is the best explanation. But what does he mean by best? Does he just mean the simplest explanation is the one that's most easily understood? Well, no, he meant the simplest explanation was our best approximation to truth. But is that true? Is it true that the shortest description of something is also the most likely to be the true description? Or in the context of machine learning, is the shortest description of the data, the most likely to be the best predictor of future data samples. And that actually is the case. There's a field of machine learning called outcome learning, and it shows that when you have a set of data samples, the most concise description of those data samples is also the best predictor of future data samples that you see. Now, just a brief overview of machine learning. The way it works is it gets a set of data samples with classification labels, and then based off of those data samples, it fits a model, and then uses that model to classify future data samples that it sees. Now, what do we mean by a concise description of data? Well, this is also formally defined in computer science by something called Kolmogorov complexity. And Kolmogorov complexity essentially is the shortest program that can represent the piece of data that you're interested in. But there's a big caveat with Kolmogorov complexity that's huge, and it is that Kolmogorov complexity is not computable. You can't algorithmically figure out the Kolmogorov complexity of your data. So therefore, you can't compute a good hypothesis, which in short means that machine learning shouldn't work, because what it depends on, which is a concise description of the data, is not computable. So you can't solve it with a computer. So why does machine learning work? Because obviously it does. I mean, there's a huge billion-dollar company, Google, that its bread and butter is machine learning. Machine learning makes Google work, and everybody uses Google. So if machine learning is not something that can be solved by a computer, but it works really well with computers, how does that even make sense? Seems like a contradiction. Okay, well, here's a bit more computer science theory. So Kolmogorov complexity can be calculated, but in order to calculate it, you have to use something that's not computable itself, which is a Turing oracle. There's another famous problem in computer science called the halting problem. And the halting problem is to determine for any arbitrary program that that program halts. This problem is also something a computer cannot solve, and you can prove that too. But if you did happen to have some entity that could solve the halting problem, at least for a certain subset of problems, then you can also calculate the Kolmogorov complexity, at least for a subset of problems as well. And as I talked about before, calculating Kolmogorov complexity is necessary for machine learning to work. So therefore, the fact that machine learning works very well is proof that we have Turing oracles solving our problems. And essentially, we are Turing oracles, because we're the only non-computational entity involved in the whole process of machine learning. So I took this observation and applied it to machine learning. And by the way, this is a very direct, non-naturalistic theory of things, because naturalism has to boil down to mathematical functions of the past. But all mathematical functions of the past can be represented by algorithms. So if you have a Turing oracle, it inherently is something non-algorithmic and therefore non-naturalistic. So this is an application of a non-naturalistic theory of reality to a very practical area of computer science. So now that we realize that machine learning uses a Turing oracle to succeed, we can apply this observation and perhaps improve machine learning itself. So normally in machine learning, the Turing oracle is queried by the person putting together the machine learning algorithm and applying it. But once that's done, that's the end of the querying of the Turing oracle, the human. The human just puts together, the programmer just puts together the algorithm and runs it, and that's it. And sometimes there's a query at the end when the person stops the algorithm from running. But imagination sampling says, why only query the Turing oracle at the beginning of the run? Why not query the Turing oracle throughout the run? If the Turing oracle is what makes machine learning work so well, then surely the more you query it, the better it will work. So imagination sampling takes the notion that machine learning works because it queries a Turing oracle and says, so why just restrict the number of times we query the Turing oracle? Why not query the Turing oracle as much as we can to make the machine learning algorithm work better? So that's the idea of imagination sampling. And to reiterate, it's a very non-naturalistic view of computer science. And so we're going to test this idea. Do humans actually function as Turing oracles? So here's a quick formal model of the problem domain. So A is the entire space of samples, the entire potential space of samples that we're trying to learn based on just a subset of those samples. And F is the target function, so it's the classification of all those samples. And we'll just say the classification is ones and zeros. One sample is 1, the other sample is 0. And so what we want to do is, based on just a few samples, figure out how to classify future samples as either ones or zeros. Now to do that, we need hypotheses. We need hypotheses about what the true underlying function is. And so the entire space of hypotheses that we'll consider is capital H, and lowercase h is a particular one of those hypotheses. K of H is the Kolmogorov complexity of H. C is the amount of A, which is the entire space of samples, that is covered by H. So that's the area that we can actually classify. And then S is a set of samples from A, and S subset C, or subscript C, is the subset of samples that are covered by the hypothesis that we can learn from. Okay, and the classification hypotheses will just be simple boxes. So A is just a big grid, and a hypothesis is a set of boxes on that grid, and each box has a classification that says everything in this box will be either a 1 or a 0. And so our goal is to optimally place those boxes on A to make the best predictions. And so H is every possible subset of boxes that you can distribute across A, and H is one of those subsets. Now, in terms of machine learning, this is a horrible hypothesis space. In order for machine learning algorithms to work, their hypothesis space has to be very, very limited. It's essentially a kind of compression, picking your machine learning algorithm. But I'm not restricting the hypothesis space at all. The multibox hypothesis space can represent absolutely everything. So if this was what a machine learning algorithm had to deal with, it would do really, really badly. The only way you can find a good multibox hypothesis is through having a good calculation of your Kolmogorov complexity. And here are some quick visual examples of what multibox classification looks like. You can see you have X's and O's. Those are your classifications of different samples in that space. A sample is just just a coordinate in that region. And then the red boxes say to classify everything in that box as a red X, and a blue box says to classify everything in that region as a blue box. And so you can see there are lots of different ways you can stick boxes on that space. And here's a quick wake up. This is a tardigrade. He's saying hi. Making sure everybody can hear me and is awake. Okay. All right, so estimating Kolmogorov complexity. So Kolmogorov complexity is not computable in general, but for particular cases you can calculate an upper bound. That's what our compression algorithms do when you compress things down into a zip file and such. So we already know that we're using a multibox classifier. So a really simple way to calculate upper bound on your multibox hypothesis is count the number of boxes. And that's going to be an upper bound. The number of boxes times some constant is going to be an upper bound in your compression. You're not going to get much bigger than that. And then you also have to factor in misclassifications in those boxes, because those count as a larger space in order to specify all the misclassifications. Alternatively, since we know that a good compression leads to good prediction, then we can estimate our compression based on our prediction. So after we've come up with a classification, we can test it out, and then based on the accuracy of our test, we can figure out some kind of bound, its upper bound, on what the Kolmogorov complexity of our hypothesis was. So even though Kolmogorov complexity itself is non-computable, we can compute upper bounds on it. All right, but this equation actually has an interesting implication for induction. So I'm getting back to the original discussion of inductivism in science and how we can actually justify the assumption that we can do induction. So this equation provides justification for induction. I know it's a bit obscure, but if you happen to remember the terminology I defined a bit earlier on, what this shows is that if your hypothesis keeps a constant Kolmogorov complexity, then as your number of samples grows, your predictions become better and better and they approach 1. So that means if you have a Turing oracle and you can compute a good, and you can figure out a good hypothesis with a low Kolmogorov complexity, you can actually make derive general principles based on a limited number of observations, because S subscript C does not have to cover all of A in order to get accuracy that's better than just randomly guessing. All right, so here we see that you indeed need a non-naturalistic theory, namely Turing oracles, in order for science to even work. If you don't have a Turing oracle, if you only have natural processes, which can be reduced to algorithms, then you can't do induction. So here we go. Here's an application of non-naturalistic methodology to science to even show that even science itself needs non-naturalism to even work. All right, so now let's apply this idea to a real problem. There's a website called Kaggle where different corporations post their data sets up there, and they let data scientists compete to come up with good models, and best model wins a bunch of money. So I picked one of their data sets, and it's a huge data set. It has 132 dimensions. The one that I was showing you before just has 2 dimensions, so that's really easy compared to this. And it has hundreds of thousands of samples. So unfortunately, I didn't come up with any breakthroughs that allowed me to win this Kaggle competition, but it at least is a real data set. So I picked 2 dimensions at random, and then I made a scatter plot of those 2 dimensions, and then I drew boxes around those samples, just visually looking at the samples and drawing boxes. And then I compared to a few algorithmic approaches. So if I am a Turing oracle, as predicted by non-naturalism, then I should do better than these other algorithms. And also, I should hopefully see this trend of increased prediction accuracy as the Kolmogorov complexity of my hypotheses remains constant. So here's an example of the kind of boxes I would draw on the data. You can see I try and surround mostly red X's with red boxes and mostly blue with blue boxes. Pretty simple approach. And then here are the 3 other algorithmic approaches I compared myself to. The first 2 are pretty bad. The first just draws random boxes and selects random classifications. The second takes that set of random boxes and picks a subset that maximizes a metric that's supposed to improve accuracy. And then the third is a algorithm from literature called the set cover machine. And it tries to find the minimum number of square boxes that cover as many samples of one particular classification as possible while minimizing misclassification. The problem with this algorithm is that it's in a problem domain called NP-complete. So basically, the algorithm's runtime scales exponentially as the problem size increases linearly. So very quickly, the basic algorithm becomes unworkable. So they can't find the optimum set cover, but they can still find a decent one using some approximation. However, even that approximation gets very slow very fast to calculate. It's yeah, to the power 4 on the number of samples. So as your number of samples increases linearly, the runtime increases to the power 4. So to improve it a little bit, I subsample using a square root of n. So that should reduce it down to just a quadratic increase rate. It still gets slow pretty fast, but it's at least tractable. So here's an example of randomly placed boxes. Here's an example of the selected boxes that supposedly are better. Not sure if those are really better. And then here's what the set covered machine does. You can see it picks groups of classifications that are all the same type and draws a little box around them. So it doesn't classify as many, but the ones it does classify are much better classified. All right, so let's look at results. So I did 351 trials, and I evaluated. So the way that machine learning evaluation works is you develop your hypothesis, and then you take on one set of samples, and you take that hypothesis and evaluate it on a completely different set of samples. That's important so you don't cheat and know what you're going to be tested on. So my hypotheses were overall the best, but only slightly better than the set cover machine, which is the algorithmic approach. And everybody, all these different approaches, myself and the algorithmic approaches, none of them were very, very good in general. They're pretty bad because the mean accuracy for all the approaches didn't go above 51%. So it's only slightly better in general than random guessing. The particular hypotheses were pretty good, but in general, it was only slightly better than random guessing. So I was only slightly better than these algorithmic approaches. I also saw some evidence that this generalization was happening, this induction. And that is that I saw, so it's not a very strong indicator, but you can see it a bit. You can see this graph has a general upward trend. And what this graph is showing is that as the number of samples increases, the hypothesis I came up with manually started being better than the ones that the set cover machine came up with. And if we, so that was, previous slide was just myself compared to the set cover machine and compared across all algorithms, and we look at which algorithm was the best, you can see this trend is much more pronounced. The times my hypothesis was the best shot up at a steeper rate than in the previous graph. So that is some kind of evidence that induction is happening. I am generalizing to some extent. It didn't jump out and grab me by the face or anything, but there's some kind of evidence there. Okay, and so that's the basic talk. I have some more backup slides where I simulate what a Turing oracle, how a Turing oracle would perform against a standard algorithm. But for now, I'll open things up for questions. Everyone's unmuted, so everyone should be able to talk.
Yeah, elaborating on what you went over would be good.
Okay. Let's see. We'll start with the problem of induction. The problem of induction has been formalized and commenced as no free lunch theorem. Here, I'm going to mute it real quick for everyone because I'm getting feedback. Okay, so the problem, so science assumes that you can do induction. Based on just a few examples, you can generalize. However, this is not a necessarily true belief. For example, David Wolpert, well, first you have David Hume that proved that's not necessarily true that induction would work. And then we have this formalized in computer science by David Wolpert with the no free lunch theorem, which says all algorithms are essentially equal. None of them are better than any others at generalizing. So we shouldn't expect to do any better than just randomly guessing. But we are pretty sure that we do a lot better than random guessing when we learn about the world. So if our minds are just algorithms, then we shouldn't be able to do induction. We shouldn't be able to do science. The simple argument here is that we are able to do science. So we are able to do induction, so therefore our minds are not algorithms. So right there we have a very simple argument for non-naturalism. Naturalism would mean science doesn't work. Science does work, so therefore naturalism is false. And then the rest of that talk is just taking that observation and applying it to machine learning, because this is exactly how machine learning works. Machine learning tries to do induction, learn a general model for making predictions based off of just a few observations. But if all we had was algorithms, that wouldn't work. And we can see using a subfield of machine learning, Occam learning, that machine learning works because we are Turing oracles. You have to have the input of a Turing oracle to find a good, concise description of your data for machine learning to work. So if you need a Turing oracle to make machine learning work in the first place, then surely the more often you include a Turing oracle in machine learning, the better it will work. So in that case, I decided to test this with myself as a Turing oracle and see if I could outperform other algorithms on a data set. And so this was just a definition of the data and problem and the algorithms I was using. This is a tardigrade, which is a creature that can survive in pretty much anywhere, even deep space. And then I also showed this interesting observation that we can show mathematically that if you have a Turing oracle, you can do induction. And remember before we were showing that if we didn't have Turing oracles, if the human mind is just algorithm, you can't do induction, therefore you can't do science. And so if we can do science, then we must be Turing oracles. And here we have a mathematical demonstration of that fact. If you do have a Turing oracle, then as you get more observations, you're able to make better and better predictions, better than just random guessing. And so that was an interesting thing that we derived mathematically. And we're trying to test that out empirically. Do empirical observations match our mathematical derivation? So again, myself as a Turing oracle, I wanted to see if I could outperform a algorithmic approach, which if Turing oracles are what make algorithms work, then that should be true in some way. And I also wanted to see if I was doing induction. Was I generalizing based off of a few observations? So here are some examples of the algorithmic approaches and myself. And it turned out that I was a little bit better than algorithms. And none of these approaches, myself or the algorithms, were all that great, but still I was a bit better, enough to be statistically significant. And we did see some generalization taking place. So if generalization was taking place, then we would expect the Turing oracle to perform better and better as the number of samples increased. And that's what we saw. We see this a little bit in this graph where there's a slight upward tendency where I start outperforming the algorithm as the number of samples increases. And it becomes more pronounced when we compare myself to all the different algorithms and the set cover machine to all the algorithms. So, I mean, it's not a glaring piece of proof, but it's still definite evidence that a human myself operates as a Turing oracle. Well, I think we are Boolean Turing oracle. David had asked the question, to what degree do you think we match the definition of a Turing oracle? I'm guessing this is fuzzy, not Boolean. I would say it's Boolean, but I don't know if we are a complete Turing oracle or just a partial Turing oracle. So a complete Turing oracle is one that can solve every single instance of the halting problem. A limited one, a Turing oracle, is a Turing oracle that can solve a limited subset of the halting problem. So it's more like subset or full set than fuzzy or Boolean, because it's still Boolean. We can still definitively solve some variants of the halting problem, just not everyone necessarily. Although given enough time and resources, maybe we can solve everything. Okay, so that was recap number 2 of the talk. Anyways, I thought this was interesting, not just because I made it, but I thought it was interesting as an application of non-naturalistic theories. So I wanted to show that non-naturalistic theories of things can actually be applied, and you can potentially make some good progress with a non-naturalistic methodology. So basically I wanted to get it out of just talk of philosophy and what's the correct philosophy of science and all that, but to show it actually does make a very tangible difference in what we do. And hopefully I've succeeded there. Do you guys think I did, or do you think it just made assumptions that weren't founded? I don't know. And this is also what I want to see intelligent design advocates and others do a whole lot more of. I think it'd be really interesting if intelligent design figured out different ways like this to apply intelligent design. I'm sure lots of the critics would be interested in this as well. The more we can get the intelligent design into tangible results, tangible things people can test, make predictions, do science with, the more people actually do intelligent design instead of just complain about it. And earlier, I think Angus or Arminius Manouge asked me what kind of guidance I could provide for naturalism and non-naturalism, and I would say probably the number one thing is application. If we have non-naturalistic theories or methodologies, we need to apply them. Apply them as much as we can in as many ways as we can. And that's also why I made the point in my earlier talk that non-naturalism should be a really widely impacting view of the world. Since most of our disciplines are very influenced by naturalism, if we have a non-naturalistic theory about how things work, it should also impact everything. So yeah, we should, I mean, the whole biological history, Darwinism versus creationism and such is very important, but I think we should also look for as many different places to apply our ideas as we can.